Let's discuss the linked answer question for 52 and 53. Okay, and this is from test 4, and the topic is theory of machine, vibration part basically. Okay, so electric motor, what is given? Let's read out. The electric motor turns an electric flywheel which is equivalent to an unbalanced mass of 0.125. Okay, unbalanced mass of 0.125 kg located at 250 mm from the axis of rotation. So you have a motor, okay, which basically has an unbalanced mass. I mean, just to simulate this flywheel, the eccentric flywheel is equivalent to an unbalanced mass from the center of the motor, and that is represented by eccentricity E, and this is 0.25 meters from the axis of rotation. Now this motor, what they are doing is they are keeping it on a simply supported beam which is massless. So this beam is massless, okay, but it's a simply supported beam. Okay, and so the static deflection of the point of the beam where the motor is placed, so that deflection is represented by delta, and that is given as 25 mm. Okay, so let me just convert in meters. 0.025 meters. Okay, so this entire thing I can take it as the mass m of the motor on a spring, and the spring stiffness be k. Okay, so this the static deflection is given. Okay, so beam is basically, it provides elasticity but it's massless. That's given in the problem. So that's why the entire beam is represented by a spring. So for this part I can now write it as mg as k into delta, which is delta is my static deflection. So m, the mass of the motor, is given as 75 kg. Okay, so I can find out k now. So 75 into g is 9.81. 9.81 is equal to k into static deflection, which is 0.025. Okay, so this gives by using a calculator I can find out k. This gives to be 29430 Newton per meter. Okay, so now this is basically a single degree system where mass is placed on a spring, and therefore the natural frequency for this system, omega n, is given by root k by m, k by capital M, where m is the mass of the motor, capital M is the mass of the motor. Okay, so let's substitute the values and get the natural frequency. So this value comes out to be 19.80 Hz. Okay, so now, so this is, I mean, when the forcing frequency or the forced frequency because of the unbalanced mass, if that equals to the natural frequency, then resonance happens. Okay, so that is the condition for resonance. Okay, so my 52, the answer for 52 is the angular velocity at which resonance will happen is when it becomes equal to my natural frequency 19.8. So the answer is B. So now let's see the question for 53rd. The minimum angular velocity for at which the amplitude of the steady state vibration is 6 mm. Okay, so now this spring mass model, we have an eccentric flywheel, so that basically creates an harmonic force which is nothing but F0 sine omega t, and the amplitude of this harmonic force is basically the me, unbalanced mass, into eccentricity into omega square into sine omega t. So F0 is basically the amplitude of the force, which is me omega square, and which is nothing but 0.125 into eccentricity. Eccentricity is 0.25 into omega square, which I don't know. Okay, and now so this is basically a forced vibration on a single degree system. So the amplitude is of this steady state harmonic vibration. The response is basically given by f naught by k root over 1 minus omega by omega n whole square plus 2 xi. This is a general formula, but xi represents your damping, but there is no damping in this, so this factor becomes 0. And so I have, because this root is there, so I have plus or minus f naught by k by root over, the root gets cancelled because there is a square, so you have 1 minus omega by omega n whole square. Okay, so what we'll do is, now we'll try to simplify it further. Okay, so my amplitude basically becomes equal to my amplitude will be basically becoming equal to f naught by k plus or minus 1 minus omega square by omega n whole square. So this is my x, and this becomes equal to plus or minus. So now f naught I have found out, which is me omega square. Okay, and so now let's substitute all this into x, and x, the amplitude will become okay, so me omega square by k by 1 minus omega square by omega n square. Now another thing is, omega n square was k by capital M, so I can substitute k as, in this case, this equation in this equation, so I'll get plus or minus me omega square by m omega n whole square by 1 minus omega square by omega n whole square. So I can just take these terms common, and so I'll get omega square by omega n square minus omega square by simplification. So there are plus and minus, so I can get the same value of x for two different values of omega because of this plus and minus. So let's take x as 6 mm, that is given, so 0.006, and let's take positive sign first and find out omega. So x is 0.006, small m is known, small m is basically 0.125, capital M is 75, and the eccentricity is 0.25 into omega square by omega n I found out 19.80 minus omega square. So this basically gives the value of omega, to be let me just use the calculator to find out omega. Okay, so omega basically I can further simplify this. I can write 0.006 into 75 by 0.125 is equal to plus or minus 250 omega square by 19.8 square into minus omega square. So this if I simplify, I get omega as 19.146. Okay, now if I take the minus sign here in this equation, so in that case, if I simplify, I get omega as 20.52 for this case. So for two values of omega, I mean this you have to just put minus sign and then just calculate by means of a calculator. You will be getting 20.52 hertz. So the same the 6 mm I can get using two angular velocity. So what is asked is the minimum angular velocity, which gives my steady state response amplitude to be 6 mm. So that is 19.146, which is close to 9.6. There might be some calculation here and there. So the answer is C. Thank you.